I've been working on several large projects recently, so I decided to take a bit of a break and start looking into this machine learning thing people have been on about for the last century. Sounds overwhelming. Turns out the basic ideas are surprisingly straightforward. So what does machine learning mean? I found a good starting point was the idea of the machine. More specifically, starting with some concepts from economics, the science of human action. Humans act to accomplish some end. We apply our productive effort to convert things in our environment into things that we want. If I want some coffee, I might take the beans, grind them, heat some water, press the water through the beans, and enjoy my drink. I applied my time and effort, the labor, to intermediate capital goods to create a consumer's good, which I consume. As humans, time and labor are limited. They may be scarce, but our desires aren't. So we really want a way to make each unit of productive effort go further, to produce more stuff more easily. Machines do this. The concept subsumes so much more than engines and industrial mechanisms. A machine is a device that reduces the amount of human effort to produce some desired end. I could replace that whole coffee routine with a single machine that does everything at the push of a button. That said, these are also machines, and the computer is a machine. The computer is a machine that manipulates memory. The data in that memory could correspond to some physical device like a nuclear reactor. More importantly, any information can be translated into data and stored in that memory. Music, novels, scientific recordings. This makes a computer an extremely important machine in a knowledge economy. In the same way we tell an embedded system controller to manipulate sensor data and generate actuator signals, we can tell that computer to process any information. The computer automates processes. If we can break down a task into a list of defined steps, we can have the computer do it over and over and over again. At first, these algorithms were fairly small and dedicated to specific calculations, like a control loop or repetitive mathematical operations. For example, when Edward Thorpe invented card counting, he used, and I quote, a high-speed computer programmed to find the player's best strategy and the corresponding expectation. The electronic calculator enabled us to dispense with many of the approximations that were needed. Branching algorithms allow us to automatize evaluations. Is the temperature too high? Turn on the cooling system. We're fine? Turn it off. That said, the inventions of man tend to expand in application. Automation is no different. There is the inevitable desire to apply computers to larger and more complex problems. And at the other end of the complexity spectrum, we find ourselves trying to automate human judgment. Many applications of machine learning seem to be the automation of individual judgment calls. Practically speaking, as the problems become more complex, they also become less well-defined. It's easy to define a possible hand in blackjack. How do you describe what parts of an audio sample are desirable and what parts are noise? How do you mathematically define healthy versus cancerous tissue under a microscope? As the relationship between algorithmic inputs and outputs becomes more complicated, programmers introduce more parameters into those algorithms. These are approximations of a system's hidden variables, values that adjust the behavior of the algorithm, but whose value can't be mathematically deduced. I like to think of them as knobs on a radio or on sound equipment. The device takes some input, an audio wave, and we twist these knobs back and forth, constantly listening to the output and refining our adjustments until we find a combination that results in a sound we are satisfied with. But we may not be able to mathematically deduce what these knobs should be set to, but I bet you could mathematically define how good the output is. Then you could just try different combinations of knobs and pick the one that generated the best output. Better yet, if we look at the possible values of all those knobs as composing a vector space, there are probably ways to optimize how we traverse through it, which would be a straightforward, well-defined, but repetitive sequence of steps to undertake, which is perfect for a computer. So we've created some other algorithm that refines the first algorithm to produce increasingly better outputs the more examples we expose it to. Put together, we have created a system that automatically improves with experience, which is learning. The precise definition, as expounded by Mitchell, is a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at tasks in T as measured by P improves with experience E. E is the example we feed the programs, P is the mathematical assessment of the output, roughly, and the original algorithm, the ones with the knobs that needed tuning, is the task T. Imagine what you could do with 1,000 knobs. 1,000,000? How about 1,000,000,000? Given several billion knobs, you could probably automate the judgment as to what sequence of words should follow a paragraph of text. Anyways, this is how I think of it. That said, I haven't yet seen a diagram like this anywhere else, so for now it's just one of mine. I'm going to assume Mitchell does it the right way. He takes a more abstract process flow view. What I think of as the main algorithm is actually a target function the performance system uses to perform its task. The critic looks at this attempt and evaluates it, giving it a grade. The generalizer looks at this grade, tweaks the knobs accordingly, and finally, it passes things to the experiment generator, which comes up with something new to test out, which could be as simple as just trying to solve the same problem over and over again. You can read the book yourself. It's a very broad definition, and there are a great many ways a designer could satisfy each of these roles. It seems machine learning isn't a specific set of techniques or algorithms. It's an abstract process that encompasses a number of different techniques, all of which are in service to such a simple goal: capturing the very machinations of cognition for the purpose of magnifying the efficacy of human labor. Mathematics can offer varied yet elegant ways of formulating each component. The artistry is in selecting which methods harmonize with each other to produce something greater than the sum of its parts. I find there's beauty in that.